Hello all, I am Srichanna Daggubati. Today I will be presenting on my research paper with Komal Dadich and J.R. Srivalsan Nair titled ScatterPlotAnalyzer for digitizing the images of charts using tensor-based computational model. We are a part of Graphics Visualization and Computing Lab at IIIT Bangalore. In this work, we will discuss our workflow to digitize the chart images for both simple and multi-class scatter plots using tensor-based computational model for data extraction. In this presentation, we will walk through the problem statement pertaining to chart digitization and its related work, followed by different components of our workflow. And then we'll talk about experimentation before we conclude the talk. We know that in today's world, charts are widely used visualizations in data analysis for efficient knowledge dissemination of datasets. These charts are predominantly available in image format on the internet and print media. We usually find these datasets originally used for generating the charts that are not available along with its images, thus resulting in a pertinent need for automating data extraction from an available chart image. The original dataset that is used for chart visualization is usually helpful in areas like chart reconstruction in high resolution format, chart redesign, and chart summarization. So generalized solution for all charts is desirable one, but this is not possible given the vastness and design space of chart creation. At the same time, solving for each chart type becomes a cog in a wheel for generalized solution. Here we focus on scatterplot, one of the chart types where information is encoded as property for geometric objects. We thus propose a semi-automated algorithm called ScatterPlotAnalyzer for data extraction of geometric objects for both simple and multi-class scatterplots. In this work, we use the positive semi-definite second-order tensor fields for computational model of image to extract the data. And we also use deep learning techniques like chart type classification, text detection, and text recognition models to aid us in data extraction process. The novelty of our work lies in analyzing both simple and multi-class scatterplots using our proposed algorithm. Our results show that our algorithm can effectively extract the data from images for different resolutions. We will now talk about related work in this problem area over years. The chart classification and interpretation have been an interesting problem that has been explored by various implementations such as revision and ChartsUsing systems. One of the primary attempts in this area is revision, which performed text type classification using feature vector generated by the geometry feature of a text, along with mark type or chart type classification using a fine-tuned AlexNet model. Whereas ChartSense uses GoogleNet to identify the chart type, followed by the connected components method to extract the bar objects of this image. Few systems like ScatterAct and ScatterScanner are confined their design space only to scatterplots. ScatterAct is a system that extracts the data from scatterplot images by mapping the pixel to the coordinate system of the chart with the help of OCR. Unlike ScatterAct, WebPlot Digitizer and ScatterScan systems require usually the user interactivity for data extraction process from the scatterplots. Few also came across the work on tensor fields that have been used for detecting features such as corners and edges in an image. In our work, we use closed form tensor voting solutions to extract the geometry of the scatter points and localize it. And hence we get the location of the scatter points, which will be the desired data. In our proposed workflow, we divide the task of data extraction into several components such as chart annotation, classification, tensor field framework, etc. We first perform chart subtype classification on a given input image using our convolutional neural network based classifier. The classified image is further manually annotated using a tool called label image to localize and label the chart components such as scatter points, text labels, chart titles, etc. This annotation helps us in extracting the chart canvas and performing the text detection and recognition. The extracted chart canvas is pre-processed through morphological operations to remove noises like grid lines, and the pre-processed canvas image is used as an input to tensor field computation and analysis processes. Finally, our system ScatterPlotAnalyzer generates the extracted data into tabular format that can be used for either chart reconstruction or redesign. Similar to chart analysis, the data extraction steps for a given chart image are specific to chart type. Hence, we use a classifier to identify the chart types. A convolutional neural network with VGGNet architecture is used to classify an input image as per its chart type. The classifier is a combination of convolutional layers, pooling layers, fully connected layers, and we finally get an output in a vector format which has the probabilities of classes it belongs to. For an input image, we resize the image to 200 cross 200 size and then feed it to a classifier. The 4 chart types such as bar, scatter point, line, and pie can be identified using our classifier. As discussed earlier, we use positive semi-definite second-order tensor fields as a geometry-based extraction approach to detect the scatter points in our scatter plot analyzer system. This geometry-based approach extracts and localizes the corners and edges of an object present in a given input image. So, in order to use these tensor fields for localizing the objects, that is scatter points in an image, we need to isolate the region that contains chart objects like bars, lines, or scatter points in a chart image. We refer this region in the image as chart canvas. Our current goal is to extract the accurate chart canvas region, that is our region of interest, to focus the pixel-wise operations for data extraction. Here we use an interactive annotation tool called label image to label different regions in chart image. Example, canvas, titles, labels, and axis regions. The graphical user interface of the tool has features for creating and adjusting bounding boxes to indicate the regions, labeling, and saving the bounding box coordinates in an XML or text format. Here, apart from clean data extraction of chart canvas, this annotation process is also used for effective text extraction process. Now, given an annotated image, we pre-process the canvas region using morphological operations and watershed segmentation process to remove the grid line. And then we highlight the contours of scatter points because the highlighted contours improve the object extraction results in tensor field computational step. For computing our proposed tensor field, we first use the structure tensor, which estimates the local structure, and the structure tensor is computed using gradient tensor, which is convolved with Gaussian filter. This structure tensor is useful for edge detection of scatter points. We now use the structure tensor as the initial votes of our tensor voting process. This tensor voting process is based on the perceptual organization of our information using votes casted by its local neighborhood. In our algorithm, we use a von Neumann or 4-point neighborhood for each pixel and use the closed form solution of tensor voting to compute the tensor voting fields. Now, these eigenvalues of these tensor voting fields give the saliency values of the pixels, that is likelihood value of a pixel to be a line or junction feature. Given CL and CP values respectively, the summation of CL and CP values will always be equal to 1. The pixels with the CL value near 0 are called as junction type features and are considered as critical points. We observe such points forming clusters at the centers of scatter points, and the visualization of these critical points also helps us in determining the hyperparameters of our DB-spline clustering technique more effectively. Finally, the cluster centroids that are computed are nothing but the location of the scatter points in pixel space. Now, to change these values of the pixel space to data space, we need to get the scale of chart axis from its axis labels. For this, we use text detection and text recognition algorithms to localize and extract these textual components of charts like axis labels, titles, legend, and text and other text. In chart images, we observe the text that is usually highly aliased in its raster format. And at times, we often encounter text with small font sizes, different formatting, or we come across a single character labels in chart images, which makes our text extraction process more challenging. We also find different orientations of similar elements in a single chart image. Example, the title is in a horizontal orientation usually, whereas y-axis labels are found in its vertical orientations. We may sometimes encounter the labels for x and y-axis at 45-degree orientations because of its long tick labels. Given all these characteristics of textual content, we use a predefined deep learning based OCR model, namely craft text detection model, which is used for effective text area detection given its affinity and region scores. The chart text detection model is used along with its unified framework called scene text recognition model for better results. Once this text is extracted, the data aggregation is done based on this category of scatterplot. The interpretation of the legend component plays a significant role in the data extraction of multi-class scatter point or a single class scatter point. The existence of the legend component in addition to the number of classes provided in the legend component helps us in distinguishing between multi-class and simple class scatter point. In case we identify a chart with multi-class scatterplot, the legend colors are extracted from the legend ROI using image processing. And here we choose to use the CI-lab color space to identify the colors of scatter points and map them to their corresponding class labels in the legend. Finally, the data values extracted in pixel space are scaled to its original dimensions or units using a scale factor that is computed from x-axis and y-axis labels. And these values are tabulated along with its title information, and we finally get our extracted data table. For experiments and testing in ScatterPlotAnalyzer, we curated a dataset as a collection of synthetically generated scatter point images and the images collected from internet. For training and testing classifiers, we prepared the dataset including all 4 categories of images, that is bar, line, and pie charts. Our classifier model works with 90% accuracy for 1000 images in FigurQ dataset, and it gives an overall classification accuracy of 81% for scatter plots. We evaluate the accuracy of our system using F1 score metric mentioned by ScatterAct, in which our system reports 73% of success rate in a simple scatter plot and with F1 score greater than 0.5, which improves to 93% for F1 score greater than 0.4. Our system maintains the uniformity in F1 score of scatter plots, unlike very high and low scores in ScatterAct, which states that ScatterPlotAnalyzer never completely fails and is able to extract at least 50% of the data points correctly. In this slide, we demonstrate the subset of test case images for simple and multi-class scatter points along with their intermediate results from different components of ScatterPlotAnalyzer. The second row displays the visualization of critical point clusters obtained from TensorField framework. We can clearly see the clusters formed at scatter point locations. We can also see the clusters of closer or overlapping scatter points are hard to segregate, and hence all groups of points except one point overlapped are emitted, causing type 2 errors. The third row shows text detection in red bounding box given in an image that is further used for data extraction and reconstruction shown in 4th and 5th rows. The data aggregation table is done based on the class labels. In chart reconstruction, we use the extracted label colors of a legend But for simple one, we don't focus on the color extraction, so we use black as default color. The reconstructed chart qualitatively shows the effectiveness of our data extraction process. Along with F1 scores, we use Pearson correlation coefficient values as another metric for evaluating the effectiveness of our scatter plot analyzer. This figure shows the correlation coefficient values between the original and extracted data tables in a simple scatter plots and the images constructed using those data tables. We can see the difference between the correlation values is always less than 0.15 despite the omission errors caused because of the overlapping scatter points. In this figure, we can see the correlation differences in multi-class scatter points. In this case, besides the omission error, we can also observe misclassification errors in scatter plots of second column. Despite these errors that are causing minor correlation differences, we maintain the dependency property between the data points and their individual data point extraction in our scatter plot analyzer. Our experiment helps us to identify the success, limitations, and improvements that are required in our work. Tensor field computation can be made more efficient using parallel implementation by reducing its computational time and their individual data. We can also handle the data extraction errors by specifying the critical points using analytical choice of threshold in clustering algorithm. That gives an optimal data extraction results. Thus, the scope of our future work includes the overall performance and accuracy of scatterplot analyzer, and we also focus on fully automating our system. This is the list of key references used in our work. We conclude our talk with a brief note on scatterplot analyzer. We make use of class information of scatter points, which is encoded using color value for data extraction in both simple and multi-class scatter plots. The central theme of our system is using the second order tensor fields of tensor voting for geometry-based extraction. We also make use of deep learning based OCR to contextualize the data and to identify title and legend class information. We finally thank everyone who have helped us in evolving this idea by providing a platform for discussions, reviews, and funds. We would like to thank Mutacharya for helping us understand the difficulties faced by visually impaired. We would like to thank you all for time and attention today and close this talk with this slide. We'll be happy to take questions.